Several disaccharides are abundant in nature. Among the most common is sucrose, or the table sugar. Sucrose is formed from D-glucose and D-fructose. It has an alpha-glucosidic linkage and a beta-fructosidic linkage. The chemical name of this compound is alpha-D-glucopyranosyl 1,2-beta-D-fructofuranoside. 1,2 here indicates the connection between the glucose and the fructose residues. Sucrose is a non-reducing sugar because of its acetal linkage. Hence, it gives negative tests with Tollens reagent, it does not form ozones, and does not undergo mutarotation. Maltose is a disaccharide with the chemical name alpha-D-glucopyranosyl 1,4-D-glucopyranose. This disaccharide results from hydrolysis of starch by the enzyme diastase. The two glucose units are joined by an alpha-glucosidic linkage from the anomeric carbon of one unit to the C4 position of the other unit. Because it has a free hemiacetal, maltose is a reducing sugar. Cellobiose has a chemical name beta-D-glucopyranosyl 1,4-D-glucopyranose. It results from partial hydrolysis of cellulose. Cellobiose has two glucose units that are connected by a beta-glucosidic linkage via the anomeric carbon and the 4 position of another glucose unit. Because it has a free hemiacetal, cellobiose is a reducing sugar. Lactose is beta-D-galactopyranosyl 1,4-D-glucopyranose. This is a disaccharide present in milk of mammals. Lactose has a galactose unit connected to a glucose unit by a beta linkage. Again, this is a connection at the anomeric carbon of the galactose unit and the 4 position of the glucose unit. Lactose is a reducing sugar. You can see a pattern for our disaccharides wherein we have a reducing end and a non-reducing end. This is often used to identify the terminal locations of an oligo or polysaccharide. Galactose is at the non-reducing end and glucose is at the reducing end. In this designation, the compound is not necessarily a reducing sugar. Now to polysaccharides. Homopolysaccharides are polymers of a single monosaccharide. A glucan is made up of only glucose units. Examples are starch, glycogen, and cellulose. Heteropolysaccharides contain more than one type of monosaccharides. Examples are glycosaminoglycans, hemicellulose, and pectin. This is an illustration of a heparan sulfate proteoglycan. Heparan sulfate is a protein-linked glycosaminoglycan. A linkage region made up of 3 different sugar types can be found at the reducing end of this heparan sulfate glycosaminoglycan chain. Starch is a well-known polysaccharide. It is the storage form of glucose in plants. Starch is a combination of amylose and amylopectin. Most starches yield 10 to 20% amylose and 80 to 90% amylopectin. Amylose consists typically of more than 1,000 glucose units connected by alpha-1,4 linkages. It adopts a compact helical structure. Amylopectin is similar to amylose but has alpha-1,6 branching points every 20 to 25 glucose units. Amylopectin has a molecular mass of around 1 to 6 million Daltons. Glycogen is the major carbohydrate storage molecule in animals. It is similar to amylopectin except that branching occurs every 10 to 12 glucose units. The molecular mass of glycogen can reach up to 100 million Daltons. Glycogen is water-soluble. Starch, on the other hand, requires heating to swell and become a colloidal suspension. Cellulose are homopolysaccharides with glucose units that are joined by beta-glycosidic linkages. They form hydrogen bonds with each other to give the rigid, insoluble fibers found in plant cell walls.